Hi everyone. So this is the next installment in our discussion on the nature of light. This is the third problem that arose in the early 20th century. We just spent some time and quite a bit of detail on the photoelectric effect. Again, a phenomenon where light comes in, interacts with surface level atoms of metals and knocks electrons off. It ionizes them. And the only way to explain the results that we saw is to treat light as a particle. Wave nature cannot explain it. So the last one, if you will, came about 10 years later after Einstein's explanation of the photoelectric effect. Actually, I take that back, 15 years later, but about 10 years after the verification of Einstein's solution. And it really put the nail in the coffin of the idea that something weird is going on with light. This is called the Compton effect. You need to know some equations with it, and more than anything, we want you to understand the concepts, and we'll be focusing around a diagram that's right there. Okay, so the Compton effect is named after Arthur Compton. It came in the early 1920s, and it's a fairly simple idea. Arthur Compton basically said, all right, let's take some X-rays, which had been discovered at the turn of the century. They're called X-rays because we weren't quite sure what they were. Are they a new form of particle, like an electron or a proton, or are they just another form of light that our eye can't see? Compton took an X-ray source, not hard to come by, and basically shown it at electrons and looked at what happened. What was the interaction between, let's say, a particular X-ray and a particular electron? And so here is what the quote-unquote problem was. The waves of X-rays, right? So if we're assuming X-ray is a form of light, it's massless, it's a classic electromagnetic wave, it did not diffract around the electrons as one might expect from a wave. It didn't even necessarily reflect, if you were wondering, is the X-ray smaller than the electron? But what it did instead is something that was pretty startling. It collided with them. And that word collided is a loaded word. That tells us something very different. Collisions are associated with particles. And in the process, and this is why we would say they collided, there was a transfer of momentum and, of course, energy. Energy probably makes sense. You understand that photons have energy coming in. If they interact with something, they're going to give up some of that energy. But momentum? How on earth can you transfer momentum if light is massless? And so this builds on another concept that we haven't discussed that comes later, and that's a relativistic concept, but I'll get that in a minute. Okay, so what is the solution to observing this effect? Well, I've already mentioned it. Photons of light have momentum. It's been verified. Einstein's equations from a decade earlier had predicted this, but now we have experimental support for that. And upon colliding with electrons, energy and momentum are conserved. So even at this level, for this odd phenomenon, or esoteric phenomenon, you still see conservation of momentum. In this case, two-dimensional conservation, but that doesn't matter. We see that momentum is still a fundamental bedrock principle in physics, even though some major revolutionary changes are coming around by studying the nature of light. Okay, so let's look at some of the details of the Compton effect. So I'm going to start with the simple idea. So let's look at what's going on here. So we have a photon of a particular wavelength. On the video you can see that this is like a violet color on paper. It's just showed as a short wavelength. Here is our electron in question, and then afterwards we have a recoiling electron moving off with a certain momentum, and we have a scattering photon, and again in the video you see that it's red, which means that it shifted to a longer wavelength. And that should make sense if you think about it, because if the photon, all the momentum of the system before the collision is with the photon, afterwards some of the momentum goes to the electron, so the photon has less momentum, therefore less energy, and by Planck's law we see that we expect it to have a longer wavelength or a lower frequency. So the way you can put this all together, and this is the new equation, this is not something that's in your reference tables, but I'm including it because I think it's relevant and it's very indicative. Einstein was able to show for massless particles, okay, in other words, photons, the energy of that particle is related to its momentum by a fairly simple relationship. E equals P times C, C being the speed of light. Okay, you can work out the units of this in this to show they give joules or Newton meters, but the point is that this comes right out of relativity. It's actually a smaller part of a larger equation. Okay, so now let's apply this to Planck's law and rearrange. So we have energy. So we know from Planck's law that energy is equal to hc over lambda, or hf. And we know from relativity that it can be related to momentum as pc. And then we can see very simply that we have a relationship that says the momentum of any photon is simply Planck's constant divided by its wavelength. That's a hugely important equation, very simple, but it has a lot of implications that we'll see in the next tutorial. Okay, so we can ask then what would be the momentum of a typical photon. So here I've chosen a 200 nanometer wavelength, which I think is in the ultraviolet part of the spectrum, but it's not atypical. So it would be pretty simple. We can do this in one of two ways. We can put in the traditional SI version of H, 6.63 times 10 to the negative 34 joule seconds. Or if you go to the reference tables, and I'm not going to do that here, I could look up a more convenient way of looking in terms of EV nanometers or something like that. Okay, and I put in, you notice I gave, because typically the wavelengths are nanometers, and so we can express Planck's constant, or actually H times C in terms of nanometers, but like I said, we'll come back to that. So I'll just call this 200 times 10 to the negative ninth, right, taking care of the nano. And divide the two, and the coefficient in front is not really the concern, but the power. And we see it's 10 to the negative 27, and it's still kilogram meters per second. Okay, it's a really tiny value, but at this level, it's clearly enough to make an electron recoil. Okay, so another thing, this is new to the curriculum that we are expected to know, is then what would be the change in wavelength? In other words, going back to this diagram, if we shift from one wavelength to a longer wavelength, how much shift would we expect? So the derivation of this equation I'm about to write is fairly complex, but it's all algebra based. There's some relativity that we have to pull some equations. I'm not going to do the derivation, but understand that what we're about to derive simply comes from applying conservation momentum and energy in two dimensions, right? In other words, as we go and come in, it's all in, let's call this the x direction. When they both go out, there's still some x momentum, right? If I try to change colors, right, there's x and y, there's x and y, and we know that the y's have to cancel, the x's have to add to the original. We're not going to do all that. Okay, I'm just going to give you straight up what the equation is in that. And so we're going to solve for the shift in wavelength, which would be, I'll just put above the final wavelength minus the initial wavelength. Okay, and that's going to be equal to good old Planck's constant again, times the mass of the thing that we're colliding with. In this case, we're going to put a mass on an electron, because that's traditionally what the Compton effect is about, even though it could be other particles, times c, there's speed of light once again, and then what might not be obvious is y. It's fairly simple. It's 1 minus the cosine, right? That's where the two-dimensional part comes in, of theta. Okay, now what is theta here? Theta, if you look back up this diagram, whoops, I didn't want that. Move this out of the way, let me get my eraser. So let me clean this up a little bit. Maybe. Okay, sorry, I've got some technology issues going on here. Okay, so you notice in this diagram of the scattering, there is theta here and there's phi there. Phi is the angle associated with the electron relative to the horizontal, and theta is relative to the photon. So in this case, since there's only a theta, what determines the change in wavelength is the angle at which the photon scatters. Okay, so let's talk about a few important highlights, some of which I've talked about, and then I'd like you to try something on your own to finish up. All right, first of all, scattered photons' wavelength is always, since we're giving up energy, you have to give up some energy if the electron is now moving when it wasn't before, it has to be a longer wavelength, right? longer wavelength by Planck's law is associated with smaller energy, being consistent with having, as I said, less energy after the collision. And you could argue less frequency, lower frequency. The change in photons' wavelength is dependent on what? So if you look over at this equation here, what are the two main variables? Well, H is H, C is C, and we're solving for the change in wavelength. So it doesn't matter what initial wavelength you start with. It could be red, it could be violet. The change is going to be the same independent of the wavelength. It depends on the mass of the particle, okay, and the cosine of the angle. So the photon's weight dependent on the angle, really the cosine, but that doesn't, of scatter of the photon, and we talked about that, not the electron, and it's inversely proportional to the mass of the target particle, meaning that if for a given situation, if we fired it at a proton and there was a Compton effect, the change in angle would be 2,000 times smaller, so barely measurable. Okay, so rather than do a sample calculation here, because I know you can plug in the numbers, it's pretty interesting to get a gauge of how big is the delta theta for a particular interaction. So I've linked here, and I know on paper, hopefully I've put something on Schoology to make it easier. Otherwise, you have to type in the URL into this. Hyperphysics is a lot of where I get information. A fantastic website if I haven't already talked to you about it. And you can plug in, very simply, this is the calculation box, given wavelength, and I suggest just put in 600 nanometers, and you can keep it as nanometers. And then what you can do is change the scatter angle. In other words, how much shift is there when there's a small scatter angle? And how does it change as the angle approaches 90 degrees. And what I'd like you to do is, you don't have to show any calculations, but describe the main things. What do you notice about that, especially about the relative value of the wave shift? Is it significant compared to the initial wavelength? Is it tiny? Is it somewhere between? And how does it change? I'm not looking for necessarily a specific mathematical relationship, even though if you wanted to get a little bit more technical, you could plug in like 4 or 5 values and see what relationship it is. It's not a big deal. So come in with that, and then our next topic is going to be really tying this all together.